All right. Welcome to our webinar on our quantum simulation use case, nuclear magnetic resonance. So NMR is a well-established and very important analytical tool or method in chemistry or pharmaceuticals and even quality control, where you can do things like structural elucidation, assigning of molecules. You can also do things like qualitative analysis or purity checks of your samples. You can also go on and do things like dynamical stuff, like reactions or kinetics, and go to even more complex things like in metabolomics or in quality control, where you're interested in analyzing more complex mixtures. The basic idea of NMR is straightforward. You take a sample, you put it in a strong magnetic field to induce a net magnetization. Then you use radio frequency pulses to manipulate this magnetization, and you measure the response of your sample to what you do with it with all those different magnetic fields. After a Fourier transformation, what you will get will usually look like this example spectrum that I've plotted here. And interestingly, every magnetically active nucleus in your molecule will correspond to a certain set of features in the spectrum, which allows you to do all the different things that I've described earlier, and which is kind of depicted with these different letters here. At HQS, we believe that NMR will be a very important use case for quantum computers, and we have put a lot of effort in developing different tools in this regard. And one of the tools are our HQS Spectrum Tools, which is actually a classical computing tool dedicated to simulating and predicting NMR spectra and analyze those spectra. And today, Niklas Inenkel, one of the main developers of this tool, will give an introduction to our HQS Spectrum Tools, focusing on the one side on the basic concepts and on the other side also showing you how to use it. After this, Pascal, who has already run a lot of spectroscopy-like examples on real quantum computers, will show you how to use our data and our software to bring NMR experiments on a quantum computer. And finally, I will show you how to get started with using our tools with our HQStage environment. All right, we will have Q&A sessions after each talk. So please feel free to use the Q&A feature of Zoom to ask your questions during the talks, and then we can go through them after the talk has been finished. And now, without any further ado, I would continue with the first presentation by Niklas about our HQS Spectrum Tools.
Welcome also from my side. As Sebastian just said, I will talk today about HQS Spectrum Tools, which is our Python API to solve NMR spectra. And before I start, maybe like a quick note on the prerequisites for this talk. So I will anticipate that most of you are already somewhat familiar with quantum mechanics. So I anticipate that you have like a basic knowledge in the field, but no like really fancy topics will be covered. So as long as you know what a Hamiltonian is, what spin operators are, density matrices, stuff like this, you should be fine. And secondly, as I just said, this is a Python API. So this will basically be a programmatic approach on how to solve NMR spectra. The alternative that we also provide is called HQS Spectrum. So not HQS Spectrum Tools, but HQS Spectrum itself. And this you can also use on our website. And this is basically a graphical interface that takes away a lot of the tasks that you would have to do with the programmatic approach. So feel free to check this out after the talk as well. All right. So with this being said, let's maybe go a bit further into what HQS Spectrum Tools is and what you can use it for. And first of all, what is it? Well, as I said, it's some sort of Python API. So it basically contains two Python packages. The first one is called HQS NMR parameters. which is basically just a database with NMR parameters. And what this means is that you can, from these parameters, construct a Hamiltonian, which is the main Hamiltonian of the NMR problem, and which you can see here to the right. I will go into detail on this Hamiltonian later on, but what is important to note is that this is a pure spin Hamiltonian, marked here by these I operators, which are spin operators. So the second part of HQS Spectrum Tools is a Python package called HQS NMR. And this is basically a solver which is specialized for one very specific NMR experiment, namely the pulse acquire experiment. The pulse acquire experiment comes in these three phases that I will elaborate on later. However, it's kind of important to note that this solver is kind of optimized specifically for this one example. And this is not to say that we will not work on extending this also to other experiments in the future. So next, what is it for? Well, basically, we here see kind of two use cases where you could use this, this tool set. The first one is basically a high throughput industry use case. So let's say you are some sort of pharma company and you are interested in obtaining like a catalog or something like this for all of the molecules that you know how to synthesize. And then what you might want to do for quality assurance, you might want to give your customers the option to run their own NMR experiments with their own, where you provide basically the NMR parameters, where they can simulate this kind of spectra and then compare to what they are measuring, for example. There are many other use cases, but this would be one. The other option, and probably why most of you are here, we assume, is that NMR, due to the fact that the Hamiltonian is a pure spin Hamiltonian, is really, really a good use case, or like a good potential use case for quantum computing. This is because, as this is a spin Hamiltonian, of course, the spins map perfectly onto the qubits on the quantum computer. So, with this being said, let's maybe go a bit deeper into what this experiment actually is that we are running here. And so, as I said, it comes in three phases. The first phase is a sort of preparation period. And what you do there is you place a sample with the molecule of interest, typically in liquid solution, into a strong outer magnetic field, which points typically, or which we now will let point along the z-axis. And what this does is it leads to a net magnetization in your sample. I visualize this here with this little orange arrow. And what you then do is you use an electromagnetic pulse. So this would be the second phase of this experiment. And specifically, you're using a hard pi-half pulse, which means that you can model this as a rotation of the magnetization into the XY plane. And then because you have this strong automagnetic field, what will happen is that your spins start to precess in this automagnetic field. So you get a precession in the XY plane. But because all of the spins in the molecules have slightly different chemical environments, they're slightly different coupled to the external magnetic field. And therefore, what you get is for each of these spins, a slightly different precession frequency, or like a different, different precession motion. And this leads to a unique signal from each of these spins. So when you now record the time-dependent magnetization in this acquisition period, what you end up with is this sort of time signal that you can then Fourier transform, and you end up with a spectrum like the ones that Sebastian showed you on his first slide. As I just said, this is only one of the experiments that you can run. And there are a host of other experiments that you could do. This field is extremely old, actually, like 70 years or something like this. And from spin echoes over 2D NMR, there's a lot that you can do. And basically, we are currently in the process of finding basically the most valuable candidates there to extend our toolset to. And so if you have any ideas or features that you would like to see in our software, feel free to contact us. We are always happy to get this kind of feedback. Okay. So with this being said, let's talk a bit about the actual simulation that we would do. So in order to simulate an NMR spectrum, we would have to proceed in kind of 3 phases. So the first one would be the calculation of the NMR parameters. And this you could, for example, do using density functional theory, or there are also a lot of tabulated values for this, where you can basically get them from some sort of catalog. We are currently also working on an empirical prediction method, where the idea would be that you can just draw a molecule like this, and we will present you with the corresponding NMR parameters. Once you have obtained these, you can go into the next step, which is calculating the spectrum. This is what most of this talk will be about. And then finally, you would want to analyze the spectrum. So you would try to figure out which of these nuclei are responsible for the individual features in this kind of spectrum. All right. So with this, we will talk a bit more about the NMR parameters. So the first part of this. And as I showed you on the first slide, the Hamiltonian that governs the NMR problem is the spin Hamiltonian that you see here to the right. And the 4 kind of most important aspects of this are 1, the gyromagnetic ratio, which basically tells you how each nuclei will couple to the outer magnetic field, here Bz. And then due to the chemical environment of each of these nuclei, there's an additional alteration in terms of this chemical shift, which is typically given in ppm, so parts per million, and is therefore relatively small in comparison. Now, additionally, you have back here the J-coupling, and this J-coupling basically tells you for each spin what is their interaction with the other spins in the molecule. So this is a bit abstract, so maybe let's look at this in a specific example and focus on the chemical shifts and the J-couplings. So here you see on the left a molecule, and on the right you see the corresponding spectrum. And first of all, note that you have always these kind of peak structures here that you see here. And their position is basically determined by the chemical shift of each nucleus. So each of these kind of peaks or peak structures, which we call multiplets, typically corresponds to one unique spin here in the molecule. And in this case, the active nuclei are all hydrogen, so where you see the H. And so if we count through, we see 1, 2, 3, 4, 5, 6, 7 hydrogens here in this molecule. However, we just see 1, 2, 3, 4, 5 different multiplets. And the reason for this is that the chemical shifts, which determine the positions of each of these multiplets, can be very close together, which is typically, or which is here the case. And this peak and this peak are actually just overlapping multiplets. This is also the reason why you typically want to perform NMR experiments at a high magnetic field, because at a high magnetic field, these kind of peaks or these kind of multiplets move apart from one another, and it becomes easier to determine or to analyze the spectrum. However, in recent years, there have been an increased number of also low field NMR devices, and there actually like a simulation like this can be really helpful in order to analyze a certain spectrum. Okay, so this is all I wanted to say about the NMR parameters. And next, we will talk a bit more on what we actually calculate when we calculate the spectrum. All right, so basically what we are measuring in the end is the magnetization. And here what you see is a spin-dependent magnetization in the sense that K will index each spin in the molecule. And in order to get the full magnetization, so what you would actually measure, you would have to add all of them up. So what you do now is you want to see the time-dependent expectation value of this magnetization. And this you can get by including the density matrix here. And so basically all we need to do is we need to find the time dependence of the density matrix. And this we can simply do using the Liouville-von-Neumann equation, which you can see here, and which has a rather simple solution in this case. So basically what we need now is the density matrix at time 0, and then basically just have to perform the time evolution. All right. So for the density matrix at time 0, what you use is the Boltzmann distribution in the outer magnetic field. So you basically, as I said, in the preparation period, put your sample into the spectrometer and let it equilibrate. And basically, the resulting magnetization that you get, or the resulting density matrix, is just given by the Boltzmann distribution here. Now, what you can do is then you can tailor this, or yeah, you can tailor this, meaning you get basically, if you stop after this term, just these two terms, and then because what we actually want to calculate is this magnetization, and Ix is traceless, this first term will also disappear for the actual calculation that you are performing. So the only thing that's important is this part back here. So this would be rho of t naught if we would just look here before the pulse, but actually we also have to perform this pulse. And this we do using these operators p, which basically have just this form. And what this means in effect is basically that that this operation, p times rho times p, will turn this iz operator in an iy operator, but nothing more than that. And then you would perform the time evolution. So if we put all of this together, so we put rho von t in here, what we get is an expression which looks something like this. And then here at HQS, what we do is a bit different from what you will often find in the literature, which is that we perform actually the frequency, a Fourier transform into the frequency domain analytically, which means that we have to introduce here this sum over m, which is the eigenvalues of the Hamiltonian, and the eigenvectors of the Hamiltonian, and em are the corresponding eigenvalues. Now, why are we doing this? The reason is basically that this way we can get a really nice frequency resolution. So note that there's this parameter eta here, which is a fitting parameter which tells you how broad these individual peaks are. And remember that delta L tells you basically where these individual peaks are positioned. So what you can do is you start basically in the first round with an initial guess for your spectrum, where you just place Lorentzian peaks with a very large broadening around the area where you anticipate these kind of peak structures. And then you perform one calculation of the spectrum where you put more frequency points where you expect these kind of spectral features. So you would get something like this. And then you can basically repeat this process as often as you want. So here we only do it once more. And then what we see is that we have these area where there are no peaks. And we have basically very few frequency points here, where we have a lot of frequency points in the area that we are actually interested in. So this is quite advantageous because we get a lot less frequency points that we need to calculate as we would have to do in the time domain if we would perform the full time evolution. Now, this is one part. The other part that's important to note here is that we need the full diagonalization of the Hamiltonian in order to perform this kind of, or in order to calculate this formula. So what we can do is, well, basically just perform the diagonalization. However, then what we have is a problem because we get a sort of exponential scaling as the Hamiltonian grows with exponentially with each spin that you are adding. So the first thing that you could think about is maybe some symmetry considerations. So you could basically note that if you have Ix here, the set quantum number can change maximum by 1 and the Hamiltonian is a set conserving, meaning that a lot of these transition matrix elements will be 0. So you could take care of this, and then you have a Hamiltonian which is block diagonal. So the largest block in this dimension has a linear, the largest block in the Hamiltonian has a linear dimension, which is given by this binomial factor, where m is the number of spins in the molecule. However, even this would grow way too quickly. So what we are proposing is that you perform a clustering approach. And so if you would do a simple version of this, what you could do is you take a molecule like this. This molecule is called camphor. And then you just split it in two parts, the blue part and the orange part. You solve each of them independently. And then because we are calculating here a spin-dependent, each spin contribution independently, you can make a very crude approximation, basically, of this formula. However, what you would find is that this actually gives you kind of bad results. And there's also a kind of intuitive way to think about why this is the case. So let's take a molecule, let's take one of the hydrogens in this molecule, let's say this one here. And then if you look at the blue area, that's probably, well, maybe like a quite good cluster to give a good result for this individual spin contribution coming from this spin. However, if we look at this one up here, this might not be the case because we are completely excluding these orange marked hydrogens. So what we do instead is we perform a spin-dependent clustering. What this means is that for the green one, we would maybe use this blue kind of cluster, but for the red one, we would use the ones that you see now in this orange ellipse, so including some of these blue ones. And because you now get these kind of overlapping clusters, the results that you get are actually really good. And at the same time, your largest dimension is now still this binomial factor because you still can do the same symmetry considerations, but the number of spins is just the number of spins that you allow in your cluster. And this is really traceable. So you have this binomial scaling for the number of spins in your clusters, and then basically an additional linear scaling as you have to repeat this for each individual spin. Now, to show you that this actually works, first of all, here's one example, namely for the molecule that you just saw on the last slide, camphor. And what you see here is for different cluster sizes, NC, the corresponding result. So the molecule in total has 16 spins. That's the orange curve that you see on top. And then below that, I'm plotting the results that you would get if you have 15 spins, 14 spins, 13, and so on. And the reason that you basically just see the orange curve is because the result is really, really good already at 8 spins. You might be able to see here, there are some black lines that are coming out. Now, this is obviously like the ideal case. There are cases where this will maybe not work perfectly. And we have written an entire paper on this, where it fails, where it doesn't fail. And please take a look at this. We will send out after the webinar at some point an email with all of the information on the papers and repositories that I will mention during this talk. All right. So here I'm just comparing basically against our own solver. So this is maybe not as impressive or convincing, let's say. What we still can do, though, is we can compare against existing software. And the software against which we have benchmarked our solver is called Spinish, which is maintained by Ilya Kuprov and his group. And this is a well-established MATLAB software to perform NMR or to simulate NMR experiments. Sorry. And basically, they have a bunch of examples that are public and that you can look at. And we have tried to reproduce them with quite good accuracy. So they have this one folder which is called extremes. So examples where their solver is coming to some sort of limit. And one of these examples is called phosphorus here. And then what you see is on the bottom, mirrored, is the result that Spinish provides. And then here you see our results with different cluster sizes. And if we zoom in here, we can see that already at around 12 spins, we get for each cluster, we get really good results, really comparable to what they have. And the slight differences that you see here in the spectrum might just be numerical artifacts as they are performing their calculations in time domain and with a slightly different formalism. And we perform ours in frequency domain. So the other point that I want to point out here is an argument about accuracy, right? So as I just said, we are already comparable with Spinish itself. And if we would compare to an experiment, which you can see here to the right, we are also comparable to experiment. But most of the time, nobody will actually go into that much detail to figure probably out like these individual, very small side peaks here. It's really good that they match, but very often, basically, you will see that the multiplet roughly fits, and this might just be enough already for you. in an actual use case scenario. Right. And then basically, last but not least, you could start to analyze your spectrum. You could start to visualize it, compare it with experiment. You could serialize your data. So we have a lot of toolage around this as well, or perform some sort of post-processing. There is one specific point which you can see in our front-end tool, which allows you to fix some amount of errors that you have in the simulated input data. So each so the chemical shifts, for example, have a certain associated error with them. And we have a tool called Shifting the Shifts, which you can access online, which helps you to mitigate these kind of errors. Although I will not talk about this further today. So with this, I will go to the section where we go a bit into the code. Okay, so basically, what I want to show you is a very quick and short notebook demonstrating the main purposes of this module. And there are a lot more examples in this use case repository, which I will show you at the end of this. So first of all, let's take a look a bit into the HQS NMR parameters database. And basically, this database can be just imported using, this simple Python import statement. And then the database is organized in some sort of data sets. So in this case, I will use the Gizmo dataset. And I will look into the module molecules. And then what I can do is I can print all of the names of the molecules that are in this data set. And so what you see here, we can make this a scrollable element so you get an impression of like all of the molecules that you can try out. And so remember, these are all completed or like completely valid spin Hamiltonians. So ideal for the use case if you are into quantum computing, for example, and want to play around with this. So we can check out one of these molecules in this box. So how we can choose one of the molecules simply using this kind of key that you have here. And then what we do is we just print some of the data contained in this molecular data object. So you get here, for example, the name, the chemical formula. But what you also get for a lot of them is a link to where we actually get this data from. So in this case, this is the Gizmo database. So what you see here, so you have a picture of the molecule here, and you have the experimental data down here. And yeah, feel free to check this out. So with this being said, what is also obviously included in the molecular data are the chemical parameters, like the NMR parameters, sorry, like the chemical shifts and J-couplings and so on. And what you see here are basically the chemical shifts, and you find them as tuples. The first index always corresponds to the index of the nuclei in the molecule, and then the second one corresponds to the actual chemical shift. And then also, just so we have a reference, the number of spins in this molecule is 8 spins. I will run the calculation to get the spectrum later, so you get an idea of the speed. And then we will switch to a different molecule with a lot more spins, so you get a better impression. So for the actual calculation of the spectrum, we actually don't need all of this information. The only thing we need is basically the parameters in this Hamiltonian. So what we can do is we can call the function .spin_system. And what this does is it extracts just the NMR parameters. So if we execute this, what we see is that we first have the chemical shifts here. Now we can get rid of this index that we have here first, because we are now restricting ourselves just to the active nuclei. Then we have here the J-couplings, which are also given as these tuples, where the first entry is also again a tuple with the indices of the corresponding nuclei, and then the J-coupling between them. And then we have a list of the isotopes of each of the nuclei in the molecule. All right, so what we could do now is we could transform this into a structure format. What is structure? It's basically our tool in order to, which you can use to write down Hamiltonians, or to write down, I guess. Sorry. And so what we need for this is, apart from the shifts, J-couplings, and isotopes, if you look here at the Hamiltonian, obviously also the magnetic field. So now we have this, we define this magnetic field here in Tesla, and we hand this over to a function, which then extracts the NMR Hamiltonian from this data. And so if we run this, we get a structure output, where in the first entries here, where you just see like 0Z and 1Z and so on, these correspond to the terms here up front, so the coupling to the magnetic field. And then the entries down here are the J-coupling entries. And now what you could do is you could use, for example, Qiskit, with which structure is comparable, in order to manipulate this Hamiltonian and then try to obtain your own spectrum, maybe on a quantum computer or in a different simulation, and so on. One thing to bear in mind here is that the parameters of the Zeeman term, so the coupling term to the magnetic field, become rather large. So you have 10 to the 9 here. What you can do in order to fix this is you can switch to a rotating frame of reference, where you can basically get rid, of this factor 1 here. And this is simply done by adding a reference isotope to this function NMR Hamiltonian. And what you then get is a Hamiltonian with these entries massively reduced. So this is going to be important later for the talk by Pascal, where he talks about quantum computing. So I will not go into this further. All right, so this would be the quantum computing use case. So you would extract the Hamiltonian in the structure format and then perform your calculations. But then you might want to compare it to, well, a different software. So we provide you with HQS NMR, which basically allows you to calculate the spectrum directly without performing all of the simulation steps yourself. Or in case you are not interested in quantum computing, you can simply use it directly to obtain the spectrum of a molecule of interest. And by the way, you are not just limited, of course, to the data sets or to the molecules available in the HQS NMR parameter database. You are also able to add your own molecules, of course. For now, we will stick, though, with the HQS NMR parameters database. So let's go through these steps of what you need to do in order to simulate the spectrum. So from HQS NMR, we import a function that calculates the spectrum, and then to a data class, which stores all of the experimental input that we need to give. So in this case, just the magnetic field for which we want to calculate, or for which we want to run the experiment. And so basically, once we have this object, we just hand it over to calculate spectrum together with the NMR parameters that we have obtained above. And then we obtain some result. And so let's run this. And then we can also look into the individual fields of this result. So the individual data stored in this result. And what you see here is the names of these fields. The first one is molecule parameters, which is basically just a copy of the NMR parameters that we hand over. Calculation parameters, which is a copy of the calculation parameters. And then the actual result we are interested in, which is spectrum. And now we do this, that we copy all of this result so that you can easily serialize this. And there are a lot of tutorials on this in the use case repository. But basically, there's just like one function call that you can do, and then you store it into a JSON file. Right. So finally, we would like to plot the spectrum. For this, we can use the visualization module and just import this function. And then we can run this, and we get the spectrum out. All right. So this is most of what I wanted to say. The only thing I want to show now is that for a larger molecule, we are still very fast. So what I want to do is we comment this out, and then we import this molecule. And now we run everything. And now we have 40 spins in our molecule. And what we end up with is this result. So this is extremely fast because the molecule that we are interested in, we can actually look at it up here on this link. It loads, yes. Is actually quite like the individual hydrogens that are active are quite far removed from one another, and therefore this clustering approach works really, really well. We are very fast. And if we compare this result down here to the actual result that we get out, sorry, I'm scrolling a bit much, but I hope this is okay, that we get out here. So again, we compare it to the experiment. We see that this actually matches quite well. So here. Okay. So if you want to try this for yourself, there's HQStage, which is our website where you can basically get all of these tools. Sebastian is going to talk more about this later. And we have a use case repository, which is basically just a collection of all of the notebooks that we use as tutorials for these tools. So you can click here on HQS Spectrum Tools. And then what you find are basically a bunch of these Jupyter Notebooks, which are all executed. So let's say we open this one. We can actually see the result of each individual code cell. So you can get a good impression of what these tools can do just by going through this repository. All right, and then just some points on what is in this repository. Basically, you will learn how to navigate the HQS NMR parameters database, how to add your own molecules, how to customize the solver to your own needs, and then how also to compare, for example, to experiment. And with this, I'm basically done. Are there any questions now?
All right, thank you, Niklas. So I have one question here. Why is the Hamiltonian in the structure format called Pauli Hamiltonian? And are there different types of Hamiltonians available in structure?
I guess that's more.
I guess I can answer, maybe I answer this question. Yes. So in structure, we have called the representation of spin-like objects Pauli Hamiltonian, as there's a slight difference between the Pauli matrix and the spin operator, mainly a factor of 1/2 or h bar half, if you have this in. And we decided to have the Pauli matrices or the Pauli operators represented in structure and not spins. And we wanted to be clear that there's no factors of 1/2 anywhere in the matrices you get out. That's why it's called Pauli Hamiltonian. And in structure, we also have other types of particles available. In particular, we have a representation for fermions, and we have a representation for bosons and mixed systems of these different types as well. And if you're interested, I would recommend to just check out the GitHub repository of structure, which is open source and has also a quite interesting documentation. All right. I have another question. Can you explain how you reduce the size of the coefficients from 10 to the power of 9 to 10 to the power of 3?
Oh, sure. So basically what you are doing is you are switching to a rotating frame of reference. So if you look into the Hamiltonian, what you see is that you here have the gamma L, which is the geomagnetic ratio, multiplied times this factor 1, right? So what this means is basically in a laboratory frame, you are looking at these spins processing, and they are processing with a frequency proportional to this gamma L factor. And then what you do in the rotating frame is you are basically subtracting this kind of factor of gamma L times Bz, so times the magnetic field. And the only thing you are left with is gamma L times delta L times Bz. And delta L is in units of parts per million, so 10 to the minus 6. And this gives you this exact factor of 6 that you see here. So here we have 10 to the 9, and then here we have 10 to the 3. If you are interested in the exact formulas, there is, it would go a bit beyond what I want to talk about today, but this is like a very fundamental thing in NMR. So you will find a lot of resources on this. All
right, thank you, Niklas. So seems like this have been all questions for now. So thank you again, Niklas. And now that we've seen how we can get NMR parameters and how we can solve them classically using HQS Spectrum Tools, next up is Pascal, who will show you how you can get from these parameters to something you can run on the quantum computer. So, Pascal.
All right. So as Sebastian mentioned already, so I'm going to show how we can calculate NMR spectra on a quantum computer. And we have here a very basic script that basically shows how to do that. And also this script is also available on our GitHub repository. So basically when you go to GitHub of HQS and then to HQStage examples, then there's this folder that also Niklas just showed. And then I'm going to talk about this example 10 that basically calculates NMR spectrum on a quantum computer. And so this script also is runs. So if you clone the repository, you have to install a few packages, but these are all open source packages. So basically, it's only mainly Qiskit and again structure, and then you can run the script and basically start doing simulations of NMR spectrum, how you do it on a quantum computer. Also, let me mention that so this script is very basic. It is more like a playground that you can start to extend. And so what we are going to do here is we look into a small molecule. It's called cis-3-chloroacrylate acid, and it's shown here. And it has basically this chlorine here, then 2 oxygens and 3 carbons, and 3 hydrogens. But in a solvent, this hydrogen is basically exchanged with the solvent. So you will have only a spin Hamiltonian that has 2 hydrogens. So it's a very, very small molecule. But as Niklas showed, we have this database called HQS NMR parameters, where you can find also many other molecules, also with many more spins. And if you, so if you really would like to follow along this notebook, yeah, you can find more information following these links. So these links will bring you to the documentation of HQS Spectrum Tools. Then another important link is this paper from last year. So this basically shows how you calculate this NMR spectra on the quantum computer. And yeah, and finally, I put here the link again to HQS NMR parameters in case you would like to get simulate larger molecules. Okay, then, so if you would like to run this, you first need to install these relevant packages. You import the relevant objects, and then for this notebook here, we have provided the molecule in JSON format. And yeah, you can then simply run this cell to import it. And here we see again that this Pauli Hamiltonian, so this is again the Hamiltonian in structure. And the notation here is that we have the nuclei energy of the first and second nuclei, and then the coupling between the 2 nuclei. So this is like XX, YY, and ZZ coupling. Now, when you look at this Hamiltonian, you see like that the energies are still 2 and 3 orders of magnitude larger than the couplings. And if you do this on a quantum computer, this is a bit problematic because this would require that you have a small Trotter time step. Yeah, so we would like to be doing a Trotterized time evolution later. So the Trotter time step must be really small, and then you need many Trotter steps. And this is very difficult to do on current hardware. So what we then do is we do an additional transformation by subtracting the mean value of these energies of the 2 nuclei. And this is, I mean, this works because for NMR Hamiltonian, this always works in this form that we discuss. But in general, like if you do this transformation, that what you then subtract at the end must commute with the Hamiltonian. So yeah, this transformation is shown then in this cell. So we basically extract the Z terms. Yeah, we take the mean value here. Then we also have to store this mean value because we will use it later, because we essentially move the frequencies, but we would like to later compare with the solution of the HQS spectrum tool. So we need to take into account this. And then we create another Pauli Hamiltonian that just contains this correction. And then we subtract this correction from our original structure Hamiltonian. Yeah, so as you can see here that both objects here are Pauli Hamiltonians, and you can simply subtract them. So this is also because in structure you can do operator algebra, and but this is not. But this is only also possible for when you do, for example, multiplication, which means when you use structure, you can easily, for example, calculate commutators, which can be sometimes very useful to do. Okay, now we take this Hamiltonian. Yeah, from now on we start using Qiskit. So we transform now everything to Qiskit. We have a function that does precisely this. So it takes in the Pauli Hamiltonian and converts it to Qiskit. We get the Qiskit Hamiltonian, which here is a sparse Pauli operator. Okay, now we have set up our Hamiltonian. And now we come to the basically to the main part of this script, which is that we would like to calculate the NMR spectrum. And as I mentioned at the beginning, we are doing here a trotterized time evolution. Yeah, so to get the exact expression and see really how the iteration works, you would have to look into this paper. And there we basically explain in more detail how to get the expectation values that we need to solve on a quantum computer. And the result there is basically mainly this formula 1 here. Yeah, so you see here that we have to calculate the trace over the magnetization in x and y direction at time t multiplied with the magnetization, so total magnetization x direction at time t0. And then to evaluate this expression, I mean, you have to select a certain basis, yeah, because you have to calculate the trace. And if you choose the eigenbasis of the x operator, yeah, then you can write this down in this way. Yeah, so these are the eigenstates of the magnetization x direction. And yeah, what we see here is that we can then initialize. So there are basically 3 steps that we will have to do. One is that we have to initialize the qubits in the eigenbasis of the operator in x direction. And then we do a time evolution, a trotterized time evolution. And then we measure in x and in y direction. Or let's say in a real quantum computer, you would have to run a circuit twice because you measure once in x and once in y. But these are basically the 3 things that we have to do. So we have to do the initialization, we have to do the trotterized time evolution, and then we have to do the measurement. And in the following, exactly these 3 steps we will do. So we will define the trotter circuit. Here we use Qiskit for this. In this case, we do a first order trotterization. Yeah, we get our circuit here. Then we define the observables, and as we know from the expression above, we have to calculate the observables in x and y direction. So we define here this observable in x and y direction. And then we have to also define our initial state. And yeah, as I mentioned, this initial state is an eigenstate of the x operator. And yeah, you can do this by simply applying Hadamard gate or a rotate y gate by an angle of pi/2. Now, since we have here only 2 spins, this is so the creation of the initial state is rather simple because it's basically just 1 initial state. But if you have larger molecules, one would have to add here many more initial states. Okay, and that's basically all what we need to do the simulation. Yeah, so we then do the simulation here. We use the Qiskit estimator for this. And then we have to calculate our final expression for this expectation value here. So we have to, yeah, basically sum here in principle over all initial states. In this case of 2 spins, it's rather simple because there's only one initial state. And then we get basically this expression here, which I call here as Cxx and Cyx. And then we can basically plot the results, so how it looks like. And yeah, we see here that we get some oscillations and the signal decays. And the decay comes here because we added a small, some small exponential decay. Okay, and in the last step that we have to do is that we have to find the spectrum. And as we've seen also before, we have to do a Fourier transformation for that. And how this is done and why it looks like this here. So this is basically the expression that we have to calculate. Again, I can recommend looking to the paper here. But we have here defined basically the function to do that. Here they are called time signal to spectrum, which basically takes in the time signal that we have here calculated and calculates the Fourier transformation. So if we execute these cells and then calculate the spectrum, we get our spectrum here, and then we can also compare it to the results from HQS Spectrum Tools, where we basically calculated how Niklas presented it, like basically going to Fourier space, and then we can compare the results. So we can plot them, and we will see here that the results nicely agree. So that's basically all I wanted to say here already. So let me also mention that, as I said at the beginning, it's a very, it's a basic script, but you can start playing around here. You can think about how one can add all initial states, how one can play around with noise, so adding noise to the simulation, so device noise. One can also set it up so that it really runs then on hardware. Okay, and I think with that, we continue with Sebastian.
All right. Thank you very much, Pascal. So we have a couple of questions for you. So first question, do I have to change much when I do this calculation on real quantum computing hardware instead of using a simulator?
I think that there has not much to be done in principle, because we have the circuits here and everything is already in Qiskit. One thing you have to do, of course, is you have to look into what is the gate set that you would like to, where you would like to run the circuits, and then you have to do the decomposition into this gate set. But then you can run it, I think, very straightforwardly. Also, we have several backends, so for example, that you can use to run. So, for example, we have backends for AWS or for IBM, and with that you can easily connect to run on real hardware.
All right, thank you very much, Pascal. And then we have two questions that again go more in the direction of the system Hamiltonian, I guess. And in particular to the rotating frame stuff. So one question, why should the shifts of 0 set and 1 set be of the same order?
Also, this is mainly related to the trotterized time evolution that we are doing. So when you basically take your Hamiltonian and you write down the trotter circuit, then there's also a trotter error. And when you have when your energies are quite different, then basically a rough estimate is that you take the maximum element of this Hamiltonian, you multiply with the trotter time step, and this value that you get, I mean, it's dimensionless, that should be smaller than 1. So ideally much smaller than 1. So meaning that if you have large energies, then your trotter time step must be really small. But then you, to see, let's say, a real signal, or let's say oscillations like we see here in the time evolution, then this requires, because you have a small trotter time step, you have to do many trotter steps. And every trotter step has a certain number of 2-qubit gates. So you will get many 2-qubit gates and you will get a lot of noise. And this makes it very difficult to do simulations when you have very different energies in your Hamiltonian.
All right, thank you very much. And we have a question that goes in a similar direction. What if some coefficients, or what if some coefficient has 10 to the power of 9 and some have 10 to the power of 3 coefficients? And I guess the answer to this is more that on a usual NMR Hamiltonian, we have the shifts on the one hand that start with 10 to the power of 9, which can be changed by moving to the rotating frame, while at the same time the couplings are much, much smaller, but are also not affected by changing to the rotating frame. And that's why usually we can rotate away the big shifts, but we still remain with relatively big couplings in comparison. So I hope that this answers this question. And we have another question in the direction of the rotating frame. In Hamiltonian rotating frame X, Y, and Z, do these have the same values?
Yes. So in this case here, they have the same values because we basically only subtract the set components here. Right. So we, I mean, here they have indeed the same values because we take our original Hamiltonian. We only look into subtracting basically 0z and 1z terms. So these are not affected.
All right. But yes, in general, if there are large differences in the order of magnitude of the different parameters of the Hamiltonian, we have to adapt the trotter size to the smallest things that are, or to the biggest ones, and then have to run a lot of trotter steps in a simulation to resolve all the different J couplings and shifts in that case, which would be unfavorable. All right. We have another question. What are currently the main challenges for scaling to bigger spin systems?
Yeah, so I think one big challenge is, of course, that this the number of initial states, because when you go to larger molecules, you basically have to do this simulation. I mean, the number of initial states scales exponentially with the number of spins. So this is very bad. So one has to think a bit how to do this. And then also this issue is when you have different energies, like what we discussed before, that can be very difficult when you cannot, when even doing these transformations will result in energies that are quite different. But there are ways we can still get good results on a quantum computer. And yeah, I think that would be what I would say.
All right. Okay, now we're going deep. Another question, isn't it that for high temperature NMR Hamiltonian, the number of initial states would scale polynomially? And I think the answer to this could be yes. There are papers that show that you can do some kind of importance sampling on the initial states. So it should be possible to implement a method that does not use exponentially many initial states. So you don't do the full high temperature density matrix that we have there, but you try to do some kind of importance random sampling for the initial states. But this is a very interesting topic and definitely worthwhile to do more or put more research into if you want to do NMR on a quantum computer. All right, let's wait for 1 second if there are more questions popping up. Okay, so one last question and one last answer, I would say, because we are already running over time. So do we need to measure all the time points? So if you want to do a simple Fourier transform of everything, yes, but there are also methods like compressed sensing that would allow you to only measure a part, so a subset of the time points that you would like to have for full measurement. Then you have to do some more expensive post-processing, but might get away with fewer time points to sample on the quantum computer. All right. So with this, thank you again, Pascal, for this very interesting presentation. And last but not least, I will show you how you can get started with our different tools. Let me just find the correct window to share. Here we go. All right. So if you're interested in the tools that we have developed for NMR, easy way to get started, or the only way to get started, is to visit cloud.quantumsimulations.de, create an account with this register button, and of course I've done this already, so let me sign in. And once you've created an account and signed in, you will end up in this landing page that Niklas has shown earlier already, where you have two options. One is HQS Spectrum, which is our end-to-end tool with a web-based front end that you can just use in your browser. But if you're more interested in the quantum computing aspects or using the Python packages that we have, the way to go is to use HQStage. If you want to use HQStage, there are two main modes of doing this. One is a local usage where you install HQStage and the different modules that we have. Currently, this is limited to Linux, and we are currently working on macOS support with ARM machines. To get started, you can request a free trial and then follow along the documentation to install our different tools. The easier way to get started is using our online Jupyter Hub, where we have pre-installed all our different tools, and which you can just use from within your browser, no matter which OS or whatever you use. If you log in for the first time, it will tell you something about you need credits to start your server, and there will also be a button that allows you to get free credits to try it out. So you can just click this and end up with some HQS credits, and then can start our Jupyter Notebook server. On first login, this will again prompt you for your account credentials, where you just use the same ones that you used already for the cloud. And once you have opened our Jupyter Hub, you will have this examples folder available, where we have all the different examples that we've discussed today available. So there's a simple getting started example that you can run to just calculate straightforwardly a NMR spectrum using our solver. And then there are more advanced examples that you can go through. And there's also the notebook that Pascal has shown you today, which you can use as a starting point to do NMR calculations on quantum computers using our pre-computed or predefined NMR data sets as an input for the Hamiltonian. All right. For further reading, I recommend you a couple of things. So we've already talked about the HQStage examples repository, which contains the Spectrum Tools examples that we've seen today and that we've also seen in Jupyter Lab, and also has links to all the different sources of information that we have available for this particular use case at HQS. Another interesting source of information is, of course, our documentation, docs.cloud.quantumsimulations.de, which on the one hand gives you an introduction to HQStage and how to install everything if you're interested in this, and also contains a more in-depth explanation of our NMR use case, together with links to the corresponding papers and further information. So if you're interested in this, I recommend to read through these parts. And of course, there's also a in-depth documentation for the Spectrum tools containing a lot of details about the different things that we've learned today. In particular, of course, the database and how to get Hamiltonians out of this. Finally, there's our YouTube channel at HQS Quantum Simulations, where we have videos about the NMR use case, some more generic structure and so on use case videos, and also a video on how to get started with HQStage. All right, and as Niklas has mentioned earlier, we will also send an email with all the links that we've shown during this webinar later on. And with this, we are done with our today's webinar. So thank you very much for your attention. And I recommend you to get started with our HQS Spectrum tools and yeah, try to run it on a quantum computer and have fun with this. With that, bye everyone.